contrast, if you're in the superheat region, things are pretty easy. So temperature and pressure are, in fact, independent in the superheat region. So sure, if we have T and P, we can define any other piece of information we need for the thermodynamic properties. Now, within the saturation region, this might have given you a little bit of a scratch in your head to think about it. If you have pressure and internal energy, can you fully define the state of the system? The answer is yes. Pressure and internal energy are independent in the saturation region. More specifically, what you would do is you would go to the tables or the online calculator or, whatever the reference is. But I'll show you graphically what you would be doing. Is the pressure, so that's going to define our pressure, whatever, let's call this state P1 here. You would go look up for that pressure. Remember, there is a unique internal energy for the saturated liquid, and there's a unique internal energy for the saturated gas. So what you now have is the internal energy, remember, is a function of the quality of the mixture, so 1 minus the quality times UF plus X times UG here. And now you have this information, that's what was given to you, U1, and you have this information from having looked that up at the state, from the tables or from the graph or wherever you got that information, and that would allow you to extract or for you to calculate what the quality is for the mixture. Once you have the quality, you can calculate anything else that you need. So the key here is that you take pressure and internal energy, that gives you quality, and from the quality plus pressure or whatever else you're going to use, you can find anything else, whether it's enthalpy, specific volume, density, et cetera, et cetera. Okay, so that's the process. So hopefully we're getting a feel for how these state relations work, how we can determine information from tables. So now what I want to do is introduce two very common simplifications of state relations. The first is the incompressible substance model. This is only appropriate for solids and liquids. And the name says it all. If it's an incompressible substance, I can't compress it anymore. What I'm saying is that the specific volume is a constant, or if you prefer, the density is a constant. Okay, same thing. And that in that case, the internal energy is a function of, that shouldn't be a little t, that should be a capital T. Temperature only. Okay, not time, temperature. Okay, if I have that information, I can now go back and say, hey, the definition of the specific heat, remember the specific heat at constant volume was defined as the partial derivative, the specific internal energy with respect to temperature for a constant volume. But because we now know that the internal energy is only a function of temperature, it's not a function of volume for this approximation, it tells us mathematically that the specific heat at constant volume is now the simple derivative of the internal energy with respect to temperature. Okay, so what does that mean? Well, let's go back and look at CP. CP, the specific heat at constant pressure, remember, was by definition the partial derivative of the enthalpy with respect to temperature at constant pressure. But we also know that the enthalpy is, by definition, the internal energy plus pressure times volume. So we look at this expression, we say, hey, but this, we know from our model, is only a function of temperature. The internal energy is only a function of temperature. The definition of this partial derivative is with respect to constant pressure. So this mathematically is treated as a constant. And this density, or specific volume, is prescribed as constant in this model. So these are both constant. So hopefully we realize that when we have two constants, and you're trying to take a partial derivative of those constants, that in fact they drop out. And what we have is that the specific heat at constant pressure under these circumstances is identical to the definition for the specific heat. Let me erase one of those. This is, took out too many. The specific heat at constant pressure for the incompressible substance model is equal to the definition of the specific heat at constant volume. Okay, so they're identically equal for this model. So what it's saying to us is that the Cp is equal to Cv, and so we can just drop the subscripts. There is only one specific heat that is necessary for us to describe an incompressible substance. Or, if you prefer, we only need one specific heat to describe liquids and solids. All right, so having said that, we can now come back and look at these definitions and descriptions for the internal energy, and we can say, hey, if I need to know what the change is between the initial state and the final state for the specific internal energy, that's simply the integral from the temperature at state 1 to the temperature at state 2 of the product of the specific heat times the differential step in temperature. If we assume that the specific heat is constant, that the specific heat is not a function of temperature, so if we assume C is not a function of temperature, then we can make the even further simplification that the change in the internal energy is simply given by the product of the change in the temperature of the states and the specific times the specific heat of the mixture. And you can see we went from these kind of abstract concepts of specific heats and partial derivatives to something that looks really easy to use, okay? And you look at this and you say, hey, because of the assumptions of the incompressible substance model, we can take this information, go back to the definition of the enthalpy, and we can say, hey, the change in enthalpy, so recall, again, by definition, the enthalpy is U plus PV. So the change in enthalpy from the initial state to the final state is simply the change in the internal energy from the initial to the final state. And then we have plus P2V2 minus P1 specific volume 1, except, again, one of the fundamental assumptions of the incompressible substance model is that there's only one specific volume. And so I can simplify this into an expression that says this. Okay, so what we can see is that the change in the enthalpy is simply given by the change in the internal energy, which is simply given by the change in the temperature, and then we subtract off this piece of the contribution from the pressure and the density. And sometimes this portion will be really small and it won't matter. So all we care about is this portion. And what that's really telling us is that the change in the enthalpy and the change in the internal energy are the same. Okay, so these are pretty powerful approximations, but we need to remember this caveat. It is for liquids and solids only. One of the most common mistakes I will see is the inappropriate application of a model. So you say, oh, I'm going to apply this in the superheat region. No, you can't use that approximation in the superheat region, only for liquids and solids. The other common mistake that I'll see is people will you'll assume an incompressible substance, and then at some point you'll go back and say, oh, I'm going to treat the system as having a variable density. So you mix the fundamental assumptions of the model with the actual output. So in other words, you try not to make these mistakes, but don't forget that if you're going to consider the system incompressible, you have to assume the density is constant, the specific volume is constant, and the internal energy is a function of temperature only. Okay? So that gives you an introduction to a very common approximation for kind of the left side of our phase diagrams. Now let's look at the superheat region, or the right side of our phase diagrams. And what we have now is an approximation that's called the ideal gas model. And I'm sure you have seen the ideal gas equation before. It's usually introduced in typical physics and chemistry classes. So hopefully this is a little bit of a review for you. If it's not, no worries, and we'll go through this from the very basic steps. So just like the incompressible substance model had two assumptions, that the system had a constant density and the internal energy was a function of temperature only, so does a gas model, the ideal gas model. The ideal gas model says this expression has to be true, which is the pressure times the specific volume has to be equal to this product of the gas constant, that's what R is, times temperature. So we're going to introduce the gas constant. Okay. And more specifically, this is the specific gas constant. So you likely have been introduced to the universal gas constant. So the universal gas constant is denoted in thermodynamics as having the over bar above the R. And it's the specific gas constant is the universal gas constant divided by the molecular weight of the fluid. Okay, so this R bar is the universal gas constant. And it has a variety of different numbers based on what unit system that you're using. And so we'll get a chance to see those in later examples. But the universal gas constant, its name means everything. It's universal. It's the same number everywhere. The specific gas constant, its name means everything. It's very specific to the fluid you're using. So if you're using air, it's a different number than the gas constant for water, than the gas constant for nitrogen, than the gas constant for ammonia. So again, one of the most common mistakes that people make with the ideal gas model is there's probably 100 different ways for you to write this expression. I'll give you a few examples here in a moment. Make sure you're consistent in each one. So here we have pressure times specific volume. Well, I could also write that in terms of density. Okay, I can write this expression in terms of molar units. So this over bar tells me that it's the universal gas constant. It also means that that unit is on a per mole basis. So the over bar means it's that that unit or that variable is on a per mole basis. Just like the lowercase means per mass basis in thermodynamics, the over bar means on a per mole basis. So I can do this, I can do this. So just make sure that you're using a consistent set of units on all of your expressions. Okay? You've also probably seen where you separate the total volume. Instead of using specific volumes and specific densities, you use the total volume and the mass. And one last representation. Let me do this, write the expression this way, because we're going to sneak in another definition where we have N is equal to the total number of moles in the system. Okay. So again, all these different permutations and combinations of how to write the ideal gas model, make sure you're using the right one, that you have a consistent set of units. Okay, so just like we did before, we can look at these expressions and say, well, if the internal energy is a function of temperature only, then that's going to give me a simplification that I can invoke for specific heats and all that sort of stuff. But before we go there, what we want to understand is the fact that the ideal gas model has, we defined the compressibility factor that allows us to understand how close we are, how good of an approximation it is that we are treating the system as an ideal gas. So it's a check. We have a check in the system. And that's the compressibility factor. So that's this Z. So this is compressibility. Okay. So the compressibility factor, you can see, again, is essentially pick any of those forms of the ideal gas model and normalize it by itself. So what we know is that as Z, the compressibility factor approaches 1, then that means the ideal gas model is valid. As Z decreases and goes and becomes smaller and smaller, so as Z approaches 0, we know that we're having some significant, what they would say officially is that we'd have significant molecular interactions. And so the molecules actually know each other are there. And as a consequence, the ideal gas approximations are no longer valid. So we know as Z approaches 0, we have interaction in our ideal gas model. That interaction causes that approximation of the ideal gas relation, and in terms of the functional dependence of the internal energy and things like that to break down. So it's no longer appropriate. There are some advanced thermodynamic methods that you can use the compressibility factor to correct your approximations, and we're not going to cover those in this class. But what we should recognize is there are times when the ideal gas model is not valid, and the compressibility factor tells us when those times occur. Now, having said that, I want you to think about, by intuition, we know the ideal gas model is typically valid in the superheat region.